also I'm very happy to meet you here. And actually, my topic for my presentation is the example of the application of analytical chemistry to environmental science. And as you know that the chemistry is a science of almost everything, okay? And you can see the chemistry in biology, in chemical engineering, and material science, and so on. And actually the chemistry exists everywhere. However, within the chemistry, we have many branch of chemistry. For instance, analytical chemistry. So analytical chemistry is a science of separation, of a science of measurement. Right? So, for instance, if I would like to know the structure of a molecule, if I would like to identify an unknown compound, that is one of the tasks of analytical chemistry. And also the analytical chemistry will characterize to study the behavior of some compounds. Right? And however, in the probably more than 100 years ago, people only have the chemical analysis approach to study the chemistry, to study the matter. That means they need just to use some other chemical solutions to perform some reactions, and then based on the result to discover some unknown or identify some unknown. However, with the progress of the other science and technology, nowadays people more and more use instrumental analysis. That means they use some instrument, device, to study the compounds. Right? And then my work is mainly based on the instrumental application. And also we use the instrument to study some environmental topic and issues. So before we start introduce my studies, and I would like to talk about a little about of the instruments. Right? So for instance, the gas chromatography is one of the separation instruments. It can separate the specific compound from a mixture, and it uses some gas, okay, to go through to carry your analyte, your samples through a column, and those gas could be helium or nitrogen, or even in the early time the hydrogen, but hydrogen is not safe, so currently only helium and nitrogen. And high performance liquid chromatography. This is another instrument to separate. So we know that sometimes it's very hard to separate or to isolate a specific compound from a mixture, because in the nature, mixing is a natural happening actually, but if you would like to do the opposite ways, it's very hard, right? It's very hard. So for instance, this is some chiral compound, right? So they have exactly the same formula, the same elemental composition, the same structure, but just because they like the image of yourself, like your hands, right? Your right hand, your left hand, they are very similar, but they cannot overlap, right? They are mirrored to each other. So they actually are different, and they have the different impact on our human bodies as a drug, right? So for some drugs, only one type will have the treatment effect, but others don't. Others doesn't, right? So it's very critical to isolate what we want. And then that task is one of the most difficult one in analytical chemistry. However, by using some special chromatography, we can successfully isolate them apart and then use the right one. Other instrument in my study is the mass spectrometry. This is another instrument to study the structure, the Z to M ratio. That means the mass to charge ratio. Because if we would like to study a compound, a chemical molecules, if the molecule is neutral, sometimes it's relatively hard to study them. Then, so we need to ionize them to allow them to become ions. Then, because we know the ions will can be manipulated under electric field, under magnetic field. So if we change them into ions, then we can perform many different kinds of analysis. Then based on the results, based on the interaction of the ions with the electric field, with the magnetic field, then we can get much information about our compound. So this instrument is the one to study the ions. Right? So next we will talk about my research on the environment. So actually, the ideas in my study is that we all know that the pesticides are widely used in agriculture, and we also know that those pesticides could go together with the groundwater, and it could go into our drinking water system. And we also know that, that pesticides are harmful to our health, and we would like to not prevent, but to reduce the use as much as possible. And also sometimes people think that, this pesticide is safe in terms of the dosage, in terms of the amount present in our drinking water. However, one question is that because we know that the water in the water treatment plant will undergo water treatment by oxidation, by some disinfection process. Those disinfection process will produce some byproduct or degradation of those pesticides. And those degradants could be more toxic than their parent compounds. Right? That is a problem. Because initially, if you think, it's safe for some type of pesticide. However, by the treatment of the water, those previous safe compound could become more toxic, and then it will produce some health issues. Right? So our study is to do a comprehensive studies for several common pesticides to check and to monitor and determine what kind of product will be produced and their amount, what amount of the byproduct will be produced. Right. By using the separation instruments, for instance, the gas chromatography, HPLC, I just mentioned before, and also use the mass spectrometry to identify some unknown byproduct. So, just as we know, the water in the water treatment plant, several processes could be performed to kill some germs, some bacteria, and so on. And our focus is on the oxidation and hydrolysis. Right? oxidation hydrolysis. And as for the oxidation performed in the water treatment plants, it could be used the chlorine, free chlorine, and the monochloramine, and chlorine dioxide, and so on. They are listed here. Right? And we perform all of the oxidation process for 3 pesticides. And then using the separation technique to separate the byproduct, and then use a mass spectrometry to identify those byproducts. So the first pesticide we studied is the diazinon. Okay. So diazinon is used as a pesticide since 1952, and it inhibits the acetylcholinesterase. Okay. And so by inhibiting this enzyme, then some of the insects will be killed. And however, this pesticide also will affect the nervous system of human. And so our task is to identify any potential byproduct or degradants of this compound. So here is the formula of this compound. And it has a molecular weight of 304. And this is a chromatograph. So the chromatograph is some graphic results from the HPLC or from the gas chromatography or from the high performance liquid chromatography. And so we can see some of the peak. Those peaks represent a specific compound. Right? So we can see here. And also, in order to identify a specific compound, typically we will use a standard. Okay? We use a standard to compare our anode or our byproduct with our standard. If they present or if they appear in the same position here, you can see the blue one. This blue one is a standard, and the red one is one of the oxidation byproduct of the diazinon. They appear in the same time. So that could indicate that they could be the same compound. Right? It could be the same compound. And then we perform the oxidation. Okay? We perform the so here we can see the blue one is the potential oxidation byproduct of the diazinon, and the red one is the byproduct, and they appear in the same time. But that is only indicate that there is some possibility there. Okay, it doesn't mean that these two compounds must be the same one. Right? And also we perform a hydrolysis of the diazinon and also found some other peaks here. So the next task is to identify those peaks. Okay, so here is a so this is called the mass spectrum. So the mass spectrum is a graphic result of the mass spectrometry. And it shows the mass to charge ratio of those anode compounds. You can see here 153 and 289 is the mass to charge ratio. Okay, we based on this to determine their molecular weights. Right? By knowing the molecular weight, we can further identify those unknown compounds. As a result, we found that the diazonone could be oxidized to produce diazoxane here. This is one of the byproducts. And also, under the in the existence of oxidants, and the diazonone could also be hydrolyzed to produce IPMP. Okay, this is an abbreviation of a very long name of a compound of this one. Right. And and also we checked the toxicity of these three compounds, and we found that this one is more toxic than their parent compound. Right. So that provides us information about the water treatment plan or water treatment strategy. We can avoid use in some certain pH value to avoid the production of this compound. The second compound that we study is the phonophores. This is another pesticide, and also it will impact the nervous system of our human being. And however, for this compound, we didn't perform all the oxidation. We only picked the free chlorine, hydrogen peroxide, and the permanganate oxidation, and also the hydrolysis, as we will discuss later on in details. So here is just the formula of the structure of this compound. And again, this one is the chromatography. We use the mass spectrometry as a detector, okay? So to detect, to monitor any potential byproduct. And we found that this is the control. Control means that we use the phonophores without oxidation, without those process happened in the water treatment plant. We just use the compound itself. And then this is the oxidation. Okay, this is the oxidation. This is the compound after oxidation. Okay, so this is the black. Black means we don't use any pesticide. Okay, so we can see that this is a original compound, but here there is a new compound appear. Okay, but we don't know what it is. Right. So, question is what it is. And then we found that this is the anode. This is a mass spectrum of the anode. We use the mass spectrometer to try to characterize that anode compound, and we found that it has a molecular weight of 231, and this is the parent. This is the phonophores, the molecular weight of 247, and then by comparing their difference in their molecular weights, we propose that the anode compound is the phonophores oxygen analog, because before this on, we can't find any name for this compound in the literature. So it's a kind of oxygen analog because this sulfur was replaced by oxygen. Right. So its molecular weight will be less, 14 less than its original in addition to the oxidation, we also perform the hydrolysis because in the first compound, in the first pesticide, we also found that some byproduct could be produced by the hydrolysis. So we also perform the hydrolysis and also use the liquid chromatography and the gas chromatography coupled with mass spectrometry to identify any potential byproduct of the hydrolysis. And so here is the actually is the UV spectrum of the thiophenol standard. Okay, so this is actually this is a byproduct of the first ender hydrolysis, and then we check the some of the literature and found that they could be thiophenol. Okay, thiophenol. So we performed the UV determination and get the UV spectrum for on the both compounds, and we found they are almost the same, but that's not enough. In order to identify an endo compound, one approach, one method is not enough. We perform the mass spectrometry of these two compounds, right? And also we can find that this is the disulfide diphenol. This is the standard, and this is the one we got from the byproduct of our pesticide, and they show exactly the same pattern of the mass spectrum. And then we can conclude that they are identical. They are identical. So the mass spectrum is like a fingerprint of a compound, right? Because we know that nobody in the world will have the identical fingerprints so as to the compound, same to the compound. So if the mass spectrum of two compounds are identical, then we can conclude that those two compounds are the same. All right, then based on the results of our study of this compound, we propose that the pathways of this pesticide. So under the condition bigger than pH 11, okay, it will produce this compound, and then under under condition with the pH less than 11, two of these compounds will react together to form this compound, right? And the question is that this compound is more toxic than both this and this, right? So that means we need to avoid a condition or situation under with the pH under 11. The last pesticide is the Analytical, right? This is another pesticide, and with a molecular weight of 190. And also based on the literature search, we also use some potential byproducts to study whether our compound will produce those byproducts under the oxidation or the hydrolysis condition. Again, we perform the high performance liquid chromatography, and there are different oxidation. For instance, here, this is the pesticide standard. This is a free chlorine oxidation. We can see under the oxidation, all of the parent pesticide disappear. That means they has been ran out by, however, one new peak produced, right? And also under the magnet oxidation, there's another new compound produced. Then And then, also in the free chlorine, because if we check here, free chlorine oxidation, there's a new peak here. And then also another new peak here. So this is also an anode compound. And then we found that this is a mass spectrum of that anode. And we proposed that the anode compound, will have the formula like this, based on the information here. And then, by summarizing the results of our research and experiments, we propose the pathway of Analytical. Okay, so this is the parent oxidation of parent pesticide, and under free chlorine and ozone and hydrogen peroxide, and then they will produce this compound. It's called aldehyde sulfoxide. And then this compound will produce this one, aldoxycal, under permanganate. Okay. And also, this compound can directly produce this, also and then this. Right? So that means this one will produce this byproduct. However, for the free chlorine, a new compound is produced, right, with the formula here, right, with the formula. The interesting thing is that the parent compound cannot directly produce this, right, under the free chlorine oxidation. It must be this compound, right? So that means, and by checking the literature, we found this is more toxic, right? So we need, based on the information here, we can set up a new water treatment plan for some specific pesticides. All right, thank you. And this study is supported by AWW, American Water Works Association, and also under the help and the support from Dr. Craig, Dr. Adams, Dr. Nam, and Dr. Wu, and Dr. Shi. Thank you very much for your attention, and any questions?